Hi guys, in this video we'll be looking at the tangent properties of a parabola, and here are the 7 common properties that the tangents of a parabola usually follow. So we'll be trying to prove them geometrically, and there exist coordinate geometry proofs. Those are the standard proofs where you use equations and then you try to find out relationships and then you prove them based on that. But our focus will be to look at all of these 7 properties in a more geometric way, and I'll be showing you a geometric proof that will prove all of these 7 properties. So before we begin, let's give a small refresher on parabolas. If you already know that part, then you can skip that part. Okay, so I have here a parabola where it's a shape that looks like a U sort of thing, and parabolas usually have the special point called the focus and a line called a directrix. So these are not part of the shape, but these are things that the parabola comes with, if that makes sense. So this point in the focus, we can call it F, and we can call this line is the directrix. And parabolas are defined as the shape that if you were to draw a line from the focus to any point on the parabola, say P, then from the point P to the line to the directrix, you can call this one D, then the parabola can be defined as all points P. So a parabola is then all points P such that PF, this one's F, PF is equal to PD. So that is if PF is PD. What if PF is shorter than PD? Then you would be getting an ellipse. And if PF was longer than PD, then you will be getting a hyperbola. But the focus of this video is in parabolas, and so we're not really going to worry about these two cases. So that's it. That's a parabola. Alright, so here we have the 7 properties of the tangents of a parabola, and we can prove them now geometrically. So we'll be using these 7 properties as a checklist. So all of the 7 don't have a separate proof to them. It's just like one simple concept that we'll be deriving the 7 from. So we'll be using this as a checklist, and each time we come across a property that's being fulfilled, we'll go in and we'll check it. Okay, well, let's give a quick read. The first property says that the tangents drawn from the focal chord are perpendicular and they intersect with the directrix. The circle drawn with focal chord as the diameter touches the directrix. The foot of the perpendicular from the focus to any tangent of the parabola lies on the tangent to the vertex. The circle drawn with the focal segment as diameter touches the tangent to the vertex. The reflection of the focus about any tangent lies on the directrix. The tangents of parabola act as angle bisectors, and the length of tangent from the point of contact to the intersection with the directrix subtends right angles at the focus. So here we have a quick picture of the parabola with the tangents and everything, and this part, this would be our focal chord. From here all the way to here, this is our focal chord. Why? Because this is a line that's passing through the focus. That's a chord that's passing through the focus. It's a focal chord. Right. So the first thing I want you to take note is that you got to use a property of the parabolas, in the sense that from the line from the focus to any point P, right? So this is point P, this one, and from there all the way to the directrix, right here, right? So this is a directrix. This is a directrix, right? They're going to be equal. So the line from the focus to the parabola and the line from the parabola to the directrix, they are equal in length. That's the definition of the parabola. So because this one and this one are equal in length, we come with an idea that what if I can join them and make an isosceles triangle, right? There we go. There we have an isosceles triangle. Right. Now, when we have an isosceles triangle, what we can do is we can draw an altitude for the triangle. So here is approximately here would be the height of this isosceles triangle, and there we go. So because we know in an isosceles triangle, if you bisect it, the altitude is basically an angle bisector at the top. This would these two would have the same angles, which means that we have proved we have proved one of the properties which says that the tangent acts as an angle bisector. Now the only thing we left is to show that that line here, the altitude, is actually a tangent to the parabola, because that we do not know yet. What if the line goes like that? Then it's not a tangent anymore. So to show that, all you have to argue is that because it's a line, it's going to have constant slope. Is that the line is going to have constant slope, but the parabola is going to have a derivative that's always that is constant. It has a positive derivative, so the slope is going to increase, which means that the line is never going to touch the parabola again, and so that line is a tangent, and so we have proved the first property, that the tangents of the parabola act as angle bisectors. So again, we can leverage the fact that that the definition of the parabola, and say that this length here is going to be equal to this length here. Why? Because of the exact same property. Okay, and if I extend this line, if I extend the line that went to the directrix all the way to meet this other line here, which is also a tangent to the parabola, then we can see that we have similar triangles, because this and this length are equal, and you have this is 90 degrees and you have this is 90 degrees. These are going to be the same as well, because they form a Z, and right, so this green line and this black line here, they are parallel, because this triangle, so let's give them names. Let's give this F, this would be D, this would be I would call this, let's say, E, and this could be Q. Right, so QDP and FEP, they are similar triangles, and so we know that the line QD and the line FE are parallel. Right, so now if QD and FE are parallel, then we have that QD, the line QD, is also part of the isosceles triangle, which means that PQ and we can call this one D prime, that PQ and D prime are all also an isosceles triangle. Okay, so now we have that QDP, that this thing is an isosceles triangle. If that is an isosceles triangle, it means that QD is the same as D prime, which means that we have shown, because since these two triangles are congruent, these two triangles are similar, and that they have one of the same sides, then these guys are congruent, which means that the intersection has to be in the directrix, and this is obviously 90, which means that we have proven the first property, the tangents drawn from the focal chord are perpendicular and they intersect at the directrix. And if the first one is proven, the second one is also proven, because think about it, and because we all know that circle property, right, that if you have a diameter and then you draw a triangle from that, or anyway at any point of the circumference of the circle, then that's going to be 90. So second property is also proven. Similarly, you can prove the same thing for this upper triangle here. This is also 90, and you can show through the same argument that this triangle FOE is the same as this other triangle here. So show that these two are congruent, and then you can say that the intersection is going to happen at the middle, at the tangent, at the vertex, basically the x-axis. And then with that, we've proven property 2, property 3, and also you can take the same focal segment. Okay, so if you use the focal chord as the diameter, you're going to make a circle, and the circle is going to be tangent to the directrix, and that is true because this is where the circumference is going to lie. The same thing is with the focal segment. So FP is a focal segment. If you use this as the diameter and then you draw a circle, then that's going to use the tangent at the vertex as its tangent. So is also proven. Now if you look at property 5, and property 5, it says that the reflection of the focus about any tangent lies on the directrix. So the reflection of the focus will lie on the directrix, and again that is true because if you think about it, the tangent acts as a mirror, and so the tangent doesn't actually act as a mirror, but mirrors have this property where the perpendicular distance is preserved, right? So if here's my point, the image is going to look like this, but if it's over here, then it's going to look like here. So let's say I have a little stick bending to the right, and if I put that up against the mirror, it's going to look like this. It's a very bad drawing, but it's going to look like this. And what's basically happening is it's flipping the perpendicular component, but it's preserving the parallel component. And so if you look at the focus here, well, it's completely perpendicular to this tangent, and so that's just going to get flipped, but that is basically building the isosceles triangle. And so if we have shown that we have an isosceles triangle, it is literally just going to follow from the fact that we have an isosceles triangle that the reflection of the focus is going to fall into the directrix. And so property 5 is also proven. The only thing left is to prove property 7, which is that the length of the tangent from the point of contact to intersection with the directrix subtends a right angle at the focus. So basically we have to show that this all the way there, if you connect the focus to that point there, we have to show that this would be 90 degrees. We have to show that this would be 90 degrees. And so how are we going to do that? So my thought about doing this would be to use which would be to show that this triangle and this triangle would be similar or congruent, in fact. And so that we can do so by saying that this thing is a common side, it's the common hypotenuse, and we have this as an angle, and so we have that this side, right, is the same as this side from the definition of the parabola, and we can leverage one more fact. Well, because this is an angle here, and this is going to be equal to this angle through the vertically opposite angles, right? And this one is going to be equal to this through the alternate angle, and now because the whole triangle is isosceles, this is going to be equal to that, and now since this is there, again through alternate angles, we're going to have that be equal to this. And so this and this are equal to each other. So we've shown that two sides are the same and they have the same angle. So that concludes the fact that this and this are congruent. And so now that we have that, if this is going to be 90 degrees, then this is going to be 90 degrees, which means that this is 90 degrees. So done. So we've proved all 7 properties, and as you can see, all of this follows from the one simple fact that in a parabola, the distance from the focus is going to be the same as the distance from the point to the directrix. So yeah, it's always good to go back to the definition and look through from the definition and get the solution.